In this chapter, we discuss one of the key aspects for a successful deployment of SparseLand to real applications, a proper choice of the dictionary. We start with a little bit of history on this topic before diving into the more recent dictionary learning methods. The SparseLand model is built on the belief that our signals have a sparse representation with respect to a specific dictionary D. These representations are to have no more than K0 non-zeros, where K0 is much smaller than n, the signal dimension. When we are given a source of signals to treat, D is unknown and should be found somehow. How should this be done? Note that a proper treatment of this issue is of central importance for turning SparseLand into a successful model and for turning all the theoretical guarantees into relevant statements of practical worth. So what are our options when it comes to getting D? The first and the easier approach is to choose D from among a variety of known transforms, ranging from the Fourier and the DCT and going all the way to the more recent descendants of wavelets. As a side note, we mentioned that since D multiplies the representation to get the signal, it stands for the inverse transform, so one should be careful about that. A somewhat better approach is to choose a flexible and tunable transform, such as wavelet packets or bandlets, since then we could adapt them to the signals in mind. The third option is to build D from scratch by learning it from signal examples. This would be some sort of a reverse engineering process in which we aim to identify the dictionary that created our SparseLand signals by observing many realizations of them. Let's assume for now that we go with the first or second option of choosing a specific transform T as our sparsifying operation. Note that until 2006, this was the preferred approach anyway. How should we evaluate this transform's performance? In approximation theory, researchers suggested to quantify the goodness of this choice by evaluating what they call the M-term approximation error. It goes like this. We start by applying the transform T on the signal X, and then we choose the leading M coefficients while nulling the rest. The outcome is our representation, and naturally it is M sparse. We apply now the inverse transform and get XM hat. Our last step is to evaluate the distance between the original signal X and its approximated one, and pose this error as a function of M, the number of non-zeros. Naturally, all the above should be done on a corpus of signals presenting the average error as a function of M for the signal source. Clearly, the M-term approximation error is expected to decay to 0 as M grows. The speed of this decay defines the goodness of this transform for handling the signals in question. Thus, in this example, T2 is better than T1 for handling our signals. Come to think about it, all the above procedure is a bit strange. Observe that this process is based on using the thresholding algorithm as the pursuit in order to evaluate the representation. Clearly, this is not the best way to estimate alpha. So why did these mathematicians choose this approach? Because it is easier for the analysis that follows. If our goal is to get mathematical expressions for the rate of decay, we must replace the true data by a mathematical description of it. In the context of images, the model was chosen as piecewise smooth regions separated by piecewise smooth edges, where smoothness was quantified in the continuum by the availability of the first two derivatives. For such synthetic images, several transforms were analyzed. Comparing the Fourier to the wavelet, the latter clearly performs better with a decay proportional to 1 over m. Indeed, what is the best decay one could hope for? The answer is 1 over m squared, suggesting that wavelet is not that great after all when it comes to 2D signals. This led to a series of works seeking better transforms for smooth images. The contourlet and the curvelet transforms are probably the best known alternatives, giving a rate of decay that is quite close to the ideal 1 over m squared. Here is the paper that introduced the curvelet, published in 2002. The message is clear, claiming to get a near optimal rate of decay in the M-term approximation for this type of signals. So is this the ultimate dictionary for images? The answer is unfortunately negative, and this was manifested by a series of applications that try to use this transform for actual image processing needs, leading to good but not great results. Why? Because images are not that simple, and the C2 model does not really capture their true content nor behavior. This brings us to the alternative of learning the dictionary. Amazingly, this was born several years earlier, in 1996, from the research of two psychologists who studied the human visual system. The seminal paper by Olshausen and Field did not care about dictionary learning as a practical tool for signal or image processing applications. Rather, they aimed to show that SparseLand modeling is running in our heads, or the visual cortex to be exact. Earlier work by Hubel and Wiesel in the 50s shown experimentally that the simple cells in the visual cortex have a Gabor-like response. Olshausen and Field have shown that this could be explained as a sparsifying transform. So the message is, our brain believes in the SparseLand model. This is the paper by Olshausen and Field, published in Nature. The figure on the right shows the PCA basis, which is the ideal transform under the linear approximation regime. Deeper into the paper, this figure shows the actual response they got when aiming to get the best sparsification. Essentially, they trained the dictionary to represent image patches sparsely. As can be seen, the responses are local oriented edges, which are very different from the PCA. As we have already mentioned, Field and Olshausen did not care about signal or image processing applications, and their algorithm was not sufficiently effective. Later work by Lewicki, Engan, Gribonval, Aharon, Mayral, and many others brought this idea to our domain and made it far more effective. Today, this is one of the hottest topics in signal processing and machine learning. This progress is the prime reason for the great success that the SparseLand model has today, since the trained dictionaries enable to adapt this model to practically any source.